Hi everyone. In this video, we're going to be looking at the hypothesis test and the confidence interval for the difference between two means. So we have King Tut was an ancient Egyptian ruler whose tomb was discovered and opened in 1923. Legend has it that archaeologists who opened the tomb were subject to the mummy's curse, which would shorten their lifespans. A team of scientists conducted an investigation of the mummy's curse. They reported that the 25 people exposed to the curse had a mean lifespan of 70 years, with a standard deviation of 12.4 years, while a random sample of 11 Westerners in Egypt at the time, who were not exposed to the curse, had a mean lifespan of 75 years with a standard deviation of 13.6 years. Assume that the populations are approximately normal. So they're telling us this last piece because of the condition, that nearly normal condition that we have with means. So it's kind of saying you can't check whether or not this is approximately normal. We have small sample sizes, so we can't just make the assumption. They're not above 30. So typically we need to look at the data and make sure that there's no skew or extreme outliers, but we don't have the data. So they have to tell us to assume that the populations are approximately normal in order for us to use this two-sample t-test or two-sample t-interval. So we have the information here. I put it in a table that gives us the, and the X bars are gone. That's weird. So I want you to see that we have the sample mean, the sample standard deviation, and the sample size for two different populations. And again, we're looking at the difference of the means of these two different populations. And again, I wrote down the formula for the confidence interval, but again, not something that I want you to calculate by hand. I want you to see that they are taking mu1 minus mu2. So that's, again, we're looking at whether or not the values in the confidence interval are positive or negative when we decide which one is bigger. We're also using T star instead of the Z's because we're looking at student T models. So we're going to find a confidence interval. Again, this is because in your textbook, they're always going to talk about confidence intervals first, even though, again, probably don't read the textbook on this and just follow my videos. So we're going to, this is called a two-sample t-test. So the command is 2SampT, interval. I said test at first. And again, it's going to be under that stat test button. So you're going to go to stat, arrow over to tests, and it's number 0. So in this case, we're going to choose stats because we have the mean, standard deviation, and sample size. And then we're going to enter all of that information in. So I'm basically copying, again, I'm missing the bars up here. Again, we're kind of just copying what I have on the table here. Notice that we have small sample sizes and pretty big standard deviations. And we're choosing a C level of 90%, or the problem chose it for us. Oh, sorry, I want to make one more comment about this pooled right here. We are always going to choose no for pooled. So we can pool data, which is kind of a whole other calculation, when we know that the population standard deviations are the same. We don't know the population standard deviations. We almost never know that there's the same. So we're almost never able to pool anything. So it's just something that we don't study in this class. So as you are doing two-sample t-intervals or two-sample t-tests, you're always going to choose no when it says pooled. Oh, sorry, it started over. So again, it's way down at the bottom. We're entering in all the information and hitting calculate. And we have a confidence interval of negative 13.32 to 3.3184. So notice that the lower bound is negative and the upper bound is positive, which means that this interval contains 0, just like our last interval did. But these are not percents. These are the differences between two means. So this is the difference in the ages. So first, when it says which group has a higher mean and by how much, neither group has a higher mean. Like we've determined here that we don't have evidence that there's a difference between these means. And it's because 0 is in this interval. Sorry, I don't know why that does that. So we would say that neither group has a higher mean, right? So we're also not going to talk about how much. If we wanted to do a formal interpretation, we'd say that we're 90% confident that those exposed to the curse have a mean difference in the lifespan of 13.3 years below those not exposed to 3.3 years above those not exposed to that mummy's curse. So notice that I'm saying years here, not percent, and then I'm saying below to represent the negative and years above to represent the positive. So let's find the hypothesis test or conduct the hypothesis test. And if we have 0 in this confidence interval, what do you think is going to happen with a hypothesis test? It should show that there's no difference, right? Which means that we're going to fail to reject the null hypothesis. So writing the hypotheses for this, it says, let's look at the question first. It says, can you conclude that the mean lifespan of those exposed to the mummy's curse is less than the mean of those not exposed? So notice that I assigned X bar 1 to those who were exposed and X bar 2 to those who are not exposed. So when it says less than, I can just follow that symbolism. Because we're talking about means, when I go to write the null hypothesis, I'm going to use mu, not p. So this is going to be that mu1 equals mu2. And then the alternative hypothesis is I'm asking, is the mean lifespan of those exposed to the curse less than the mean lifespan of those not exposed to the curse? And again, because we got a confidence interval of 0, we should see that we're going to fail to reject the null hypothesis and show that there is no difference between the two population means. So when we run this test, we're going to enter in our information here, and it's going to look exactly the same as it did for the interval. So we're going to do a 2 sample. So it's going to be a 2-sample t-test. And we're going to put in all the information from that table. So we're going to have x1 equal to 70, x bar 1, s1 equal to 12.4, and n1 equal to 25, x bar, x bar 2 equal to 75, S2 equal to 13.6, and N2 equal to 11. We're looking at whether or not mu1 is less than mu2. And again, anytime it asks for pooled, we're going to say no. And when you run this test, so we're going to go to stat, and it's the 2-sample t-test number 4. We enter in all that information. can calculate. And you can see that we get a test statistic of t equal to negative 1.04. So about -1 standard deviations below the mean, not that unusual. So we have a p-value of 0.155, 15.5%. Remember that the test statistic, that's a t-score, that can be positive or negative, but a p-value is a probability, so it's always going to be a positive value between 0 and 1. So we got a pretty high p-value here. Again, by high, I'm talking about 15%. That's pretty high. And so our conclusion is going to be that since the p-value is above the alpha level, we fail to reject the null hypothesis and conclude that there is not enough evidence to suggest that those exposed to the curse have a shorter mean lifespan. So recall that when we did the, forgot about the assumptions and conditions, I apologize. Again, it's the same assumptions and conditions as the 1-sample t-test and the 1-sample t-interval, except for that you have to check them for both samples, including that nearly normal condition. But there's like one extra thing in here, and it's called the independent groups assumption. We need to be able to assume that the two groups are independent from each other. And that's going to come into play when we talk about Chapter 18, because in Chapter 18, we're going to do a t-test for two groups that aren't independent from each other. So looking at this problem, remember that with the 1-sample t-test, which was just the command t-test, that you could do it with either stats or data. And the same thing is different with the 2-sample t-test. So with this problem, I'm going to use data. It says the data below show the sugar content as a percentage of weight of several randomly sampled national brands of children's and adults' cereals. If there is a difference in the mean sugar content of cereals targeted, is there a difference in the mean sugar content of cereals targeted towards children and those targeted at adults? Use a 0.05 significance level. So first notice that we're talking about two different samples and that those samples are independent from each other. They're not connected in any way. So we're going to put the first sample into L1 and the second sample into L2. Both samples are random. 19 and 28, we need to assume that that's less than 10% of the corresponding populations, which would be the population of all cereals marketed towards children versus all cereals marketed towards adults. I should know how much cereal is out there, but I really don't. So then we can assume that the individuals within each sample are independent. The groups are independent from each other, and if you were to look at the box plots of these two data sets, you would see that they are reasonably symmetric, and there's no outliers. I didn't use my calculator to show that, but just put in the data and look at the box plots, just like we did for the 1-sample t-test. So when we run this test, we're going to start off with the null hypothesis, and the null hypothesis is always that the means are the same. But now for the alternative hypothesis, it's asking if there's a difference. It says, is there a difference? So we're just asking, we're not asking if one is higher or lower. It's either one. And that's when we use the not equal to. So those are going to be our hypotheses. And then we're going to do a 2-sample t-test, but this time we're going to choose data. And then we're going to let list 1 be equal to L1. And this is probably already in there and you don't have to really change anything. The frequency is always 1 for both of them. We won't do any problems where it's other than 1. Our alternative hypothesis is that mu1 is not equal to mu2. And again, we're going to say no to the pooled question. And when we run this, we will get a test statistic of 17.8. And that is crazy, right? That's 17 standard deviations above the mean. That's crazy. That's really, really high, which means that we're going to have an extremely low p-value. When you look at this in your calculator, though, the first thing that you're going to see is a 2.1, but you know that a p-value is a probability. So if you see that it's greater than 1, it's because your calculator is writing it in scientific notation. And this test statistic is so high that the p-value is extremely low, and it's written in scientific notation. It's 2.1 times 10 to the negative 21. That means that there's 20 zeros in front of that 2. Don't round this to 0. I mean, I guess if you did, I'm not going to count it wrong, but it is still a probability. It's just extremely, extremely low. So I didn't have enough room on the page to write the conclusion here. So when we go to write the full conclusion, because that p-value is so extraordinarily low, we know that it's lower than any significance level that we would ever choose. So we would say that since the p-value is less than the significance level, we reject the null hypothesis and conclude that there is enough evidence to indicate that there is a difference in the mean sugar content between cereals targeted at children and those targeted at adults. So the question is, if there's a difference, what is the difference? Before we do that, it says, if your conclusion is incorrect, what type of error did you make? Again, remember that if you reject the null hypothesis, you have possibly made a type 1 error. With a p-value this low, the chance that we made any error is extremely close to 0. So we probably did not make this type 1 error. Since we rejected the null hypothesis, what will the confidence interval look like in this scenario? Since we rejected the null, 0 cannot be in the confidence interval. Now, because we used a not equal to sign in the alternative hypothesis, we don't know if this is going to be an interval that is completely positive or completely negative. I think you could probably guess. But at this point, we're going to pretend like we don't know and say it can be either one. So let's find the confidence interval. And this comes in exactly the same way we would do a 2-sample t interval. And you pick data. And again, we would say that the list 1 is equal to L1 and list 2 is equal to L2. The frequencies stay as 1. And we have a C level of 90%. We actually should have done 95% confidence interval because this was a two-tailed test. That's my mistake. And then again, we also say no for the pooled part. And when you put this in your calculator, you will get 32.494 to 40.799. So again, you want to make sure that you look at the order in which you subtracted. And we let the children's cereal be our mu1, and the adult cereal be the mu2. So when we subtract mu1 minus mu2 and we get all positive numbers, it means that that mu1 is higher. So when we go to interpret this, we would say that we're 95% confident that cereals marketed towards children contain between 32.5 and 40.8 more grams of sugar than cereals marketed towards adults.